Nuclear chemistry. We'll talk about the nature of radioactivity. And by the way, that's a term coined by Marie Curie, one of my science heroes, and the winner of 2 Nobel Prizes. We'll talk about applications. Here are some in cancer therapy, stress test using thallium-201, cobalt-60 for cancer therapy, reaction mechanisms using deuterium. We actually talked about reaction mechanisms in chapter 14, and deuterium is heavy hydrogen. Dating historical artifacts, that's using carbon-14. We call it radiocarbon dating. This is an isotope of carbon that is unstable and decays over time. Generating electricity, which is a big debate in this country right now as to whether nuclear power is safe and what we can expect in the future. There's one other thing which I don't have on the list, and that is making and dealing with, in the modern world, nuclear weapons. And I'll have a little bit to say about that. It's certainly a topic worth discussing because perhaps for the first time in history, in the last 50 years, the world has enough nuclear weapons. And I grew up in the nuclear age. I was born in 1950, and in grade school we practiced duck and cover. We even had a song, duck and cover, duck and cover. You can find those YouTube videos that we showed up in the front of the class on an old 16 millimeter projector. And we would practice drills for avoiding the blast, avoiding that bright flash of light that could burn out retinas. So at any rate, nuclear weapons are worth some conversation. We consider this critical content for any general science knowledge. If you're going to be a citizen in this country, to not have some basic understanding of how science works with respect to nuclear reactions, that's pretty unforgivable. It puts you at a real deficit in being able to intelligently evaluate the circumstances in which you live. All right, so let's talk about, first of all, we'll start with the basics, complete atomic symbols. You were introduced to this in Chem 1. So here is the symbol for, in this case, it's going to be a radioisotope, but any element. The mass number is a superscript to the upper left, and the atomic number, the number of protons, down here in the lower left. And remember, the mass number is just the sum of the number of protons and the number of neutrons. All right. For example, here is an isotope of boron 11. And what this is saying is that boron has 5 protons. So it's got 5 protons in the nucleus. All you have to do to calculate the number of neutrons is take the mass number, 11, minus the number of protons. You get 6 neutrons. That's how we do that. And as long as there's no charge up here, the number of electrons is equal to the number of protons. So that would be 5 electrons. Okay. So there you go. 5 protons, 5 electrons, and 6 neutrons. We could also write isotopes as boron 11. If I go back to the previous slide, you can see that I've written cobalt-60. That just means the mass number is 60 for the isotope of cobalt. Thallium-201, that's its mass number. Hydrogen-2, that's how you tell that you have deuterium, because you have a mass number of 2. It means you have 1 proton and 1 neutron. Carbon-14, you have 6 protons and 8 neutrons. And that's just another way that we describe isotopes of particular elements. All right. Isotopes, atoms of an element, which vary in the number of neutrons, therefore the mass. So here's protium. This is normal hydrogen, deuterium, and tritium. And we can simply scroll on down, and we see that they all have 1 proton. That tells us it's the same element. And they have different mass numbers, which tells us these are different isotopes of that same element. Indeed, if we've got the same number of protons, we have the same element, and the mass number is just the sum of protons plus neutrons. And tritium has 2 neutrons, 1 proton, for a total of 3 for our mass number. Definitions: a nuclide is just a nucleus with a specified number of protons and neutrons, and a radionuclide is a nucleus that is radioactive. And we call radioisotopes just atoms that contain radionuclides, that is, radioactive isotopes. All right? And so types of radioactivity. Now, this isn't the sum total, but this is everything that we really need to be concerned with here. We have alpha particles, which have a plus charge of 2. It's really just a helium nuclei. So if you take an isotope of helium, just normal helium, and it's got 2 protons in the nucleus. It has a mass number of 4, and normally just an atom of helium would have 2 electrons, but if we strip those 2 electrons off, we've got a plus 2 charge, and we call that an alpha particle. Okay, so this is going to be your heavy radiation particle, this helium nuclei, which we call an alpha particle. It's got a mass number of 4, which is substantial. A beta particle is just a high energy electron, has a negative charge. It has a mass number, or an actual mass in grams, that is almost 2,000 times lighter than a proton or a neutron. And it's just literally electrons, all right? Now, we're talking here about relative penetrating power. Let me address that in just a moment, okay? Now, here we have something that is really just a high energy photon, and we call this a wow, my spelling is just atrocious. This is a gamma photon, which is a high energy photon. And you don't want to get hit with a lot of these guys, because they'll penetrate your skin, they'll penetrate your tissues, they'll go right through you, and they'll damage your DNA. 1 or 2 of them, not so bad, but if you get hit by a swarm of these guys, that's pretty bad. So the way I want you to think about the penetrating power is this. Let's say you've got a city alleyway, and here's an alpha particle. An alpha particle is like a big old semi truck, and it's going to come flying down. Now, hopefully it'll fit. What you have in city dumpsters, and some of you are country folk like I am now, but I used to live in cities, and you'll find dumpsters back there. Some people park their cars back there, and their boats and different things back there. And if an alpha particle comes through, it's going to start hitting pretty much everything that gets in its way, and it's going to slow it down. And so alpha particles, while they have a lot of mass, they're not moving that quickly, and they can be stopped pretty readily by things like clothing and paper. So in terms of getting down the alley, the alpha particle doesn't get very far. But remember, it's big and it's heavy, so it can do a lot of damage. It just doesn't penetrate very far. Okay, let's talk about beta particles. All right, a beta particle, let's just take a nice, sleek sports car. And beta particles, as I've said, these are high energy electrons. And by the way, these particles come flying out of the nucleus. And so this guy is going to go down here and it's going to weave and bob, but still, it is a car. And so if something gets in the way, it can be stopped or slowed down, but the beta particle is going to get a lot further down the alleyway than the alpha particle did. So it has more penetrating power, about 100 times that of the alpha particle. Now let's talk about the gamma particle. So gamma particle, let's think of a Hell's Angel, dude. And Hell's Angels is a bike club. I think they're out of Alameda. I can't quite remember. And this is a terrible, big Harley Davidson motor, a couple of big fatty tires down here. And this dude is going to come through. Now, this guy can dodge all the dumpsters. He can dodge the cars. I remember there was a car here which somehow got erased. Okay, there's your car. And he can dodge through, and he's going to penetrate all the way through. And if it's just one biker doing this, he'll go through and he won't do a lot of damage. But what if all of his buddies, lots of them, okay, we got a whole biker gang going through all there. Well, if you've got a big swarm of gamma rays over here, you're going to get a lot of penetration and you're going to do a lot of damage. So a few high energy photons, we get hit by those all the time, but a lot of them, that is going to be just absolutely terrible for any kind of a living organism, because we're talking about 10,000 times the penetrating power. So if you've got high energy photons in bulk going down your alleyway, you don't want them going down Main Street, folks. Relative penetrating power, there you go. 1 for alpha particles, 100 times that for beta, and 10,000 times that for gamma rays. Radioactive decay occurs when a nucleus, a radionucleus, spontaneously decomposes. Now, why are these radionuclei trying to decompose? They're trying to get stable. That is the nature of radioactivity. They decay to trying to get to some stable isotope. All right, so a nucleus spontaneously decomposes. We simply call that radioactive decay or radioactivity. And so we can look here and we can see we have uranium-238, and uranium-238 represents about 99.3% of all the uranium on the planet. There's another significant isotope of uranium, which is more unstable, called uranium-235. We'll get to that. This is not the uranium that blows up. This is not what we call fissile material, but it is radioactive, and it would be warm to the touch. So here's how we balance it. We look at the mass number. We've got 238. That's just the number of protons plus the number of neutrons. And on the reactant side, so the mass, the total mass number on the product side has to be the same. So here we have 234 plus 4. That gives us 238. So we have 238 for mass number on the product side and 238 on the reactant side. These two have to equal each other. As far as the number of protons, we've got 92 protons for this isotope for uranium, and it's going to decay to thorium, which has an atomic number of 90 protons, and an alpha particle. And if you remember, an alpha particle is just a helium nucleus. You will not always see that 2+ charge there. You may simply see that. You could see that also with a 2+ charge. There are a couple of different ways you might see this represented. Okay, so that's the simplest way to explain that. You just get the values to balance on both sides of the reaction arrow. All right, let's look at this example. Complete and balanced nuclear equations for the following fission or fusion reaction. So this is going to be a fission reaction. So what we have over here is the isotope uranium-235. Now, this is what we call fissile material, and we're going to split this isotope of uranium by hitting it with a neutron. We'll have some kind of a neutron emitter, which is going to throw out a neutron at the uranium-235 isotope. It's going to split it into these two isotopes. You've got a zinc-72 and samarium 160 isotope. Hope I said that right. And so what we're going to do is we're going to figure out, when I do this in this particular reaction, how many of these neutrons did I actually produce on the product side of the reaction. And so the way we're going to do this is we're going to take the 235, we're hitting it with one neutron, so we simply add those up. And so 235 plus 1 is 236. Over here with this particular isotope, we've got 160 and 72. And that equals 232. All right. Since we know that the mass numbers on the product side have to equal the mass number on the reactant side, we know there must be 4 of these neutrons. We don't need to worry about atomic number because this is a neutron, not a proton, so this is essentially 0. We can add up the 62 plus the 30, and that gives us atomic number, or the number of protons, 92, and we have 92 plus 0, which is also 92. Now, this is a reaction that can be used to generate electricity. It can also be used to make a bomb. You have to have about 90+% pure uranium-235. You do that. There are a couple of methods to do it. The current method is to use these high-velocity centrifuges, which separates the lighter 235 from the heavier 238, which is most of the uranium. And so you'll see this array of centrifuges where you're going through this centrifugation of uranium-238, separating it into U-238 and U-235. And it's quite a process. And we call that enriching the uranium. This is a plutonium. This is also a fission reaction. You can always tell the fission reaction because you'll have let's say one isotope over here on the reactant side. We're going to hit it again with a neutron, and it's going to produce a multiplicity of products over here. So you're taking a heavy isotope, splitting it into lighter isotopes. We call this a fission reactions. Both of these are fission reactions. Again, you can use this reaction to generate electricity, but the most famous use for it was the plutonium implosion bomb that was dropped on the city of Nagasaki during World War II, at the very end of World War II. So let's go ahead and balance this equation. So we've got 239 for our mass number for plutonium. We're going to hit it with one neutron, so we have a total mass number of 240. Remember, we have to add up to 240 over here. Now, you're not going to be able to use the mass number to tell what isotope you have here or what element you have here, but you will be able to come up with a mass number here because we have two neutrons here. So we have 144 plus 2 times 1, that's 146, and so 240 minus 146 gives us 94. That's our mass number. So I'm just going to go ahead and write that here. That will go as a superscript to the upper left, and then our element will go down here. Let's figure out what element we have. We have 94 plus 0 over here. That's a total of 94. And then we have 58. And so all we have to do is take 94 minus 58, and that's going to give us 36. And so the atomic number 36, that's krypton. So this would be the krypton 94. So that's the nuts and bolts of how you balance a nuclear reaction. All right, and I'll talk a little bit more about both of these reactions, not in terms of generating electricity, but in terms of generating fission bombs.